So in the last homework, one of the questions was to get a sense of what are the things that are confusing you, and not surprisingly enough, a third of you or so, the number one hit was, chemical potential. And that's not surprising. It's an abstract concept. I mean, I'm actually happy that maybe 2/3 of you do think that you get it. That's impressive because it's an abstract concept. And the reason it's a bit abstract is because it builds up on a lot of things. Chemical potential is not something we could have just started this semester by talking about chemical potential. In order to reach chemical potential, we had to go through a lot of concepts. And that's what makes it a bit abstract. You know, it's a crazy semester anyway. And if you're not paying attention, if you're getting lost already, it's like one of those exam problems where in order to get to the fifth problem, you must do the first four problems right. Otherwise, you can't get the fifth problem. So that's what it is. So before we really talk about chemical potential, I want to remind you, that's what I'm going to do today for like 15, 20 minutes, just to summarize what is chemical potential, because as we go further in phase diagrams, it's important we have a sense of it. So in order to get to chemical potential, we are going to do a bit of a recap of mu chemical potential and how, why we got to it. What did we do? Why did we have to invoke it and things like that? So in order to do this, our starting point always is, like in anything in first law of thermodynamics, du is equal to dq plus dw. And then we had second law of thermodynamics, and I'm going to write it in two forms. Second law of thermodynamics said that ds is more than 0 for isolated system for spontaneous change, and ds is more than dq by t for any system if it's not isolated. So you can see for any system, if you make it isolated, then of course dq goes to 0 and you recover the second formula. So thermo is really all about these two things. On top of this, even these two things boil down to some fundamental properties of the entropy, but everything else that we have done in this semester is derived from these two. These are our two axioms. You can, this should always be our starting point. Everything starts from here. And then we try to look at different settings and try to make it useful. So this equation, which is called Clausius inequality, is interesting, but we wanted to express it in certain other useful forms, right? So the idea was, well, ds is more than equal to dq by t, that's great. But what if you are carrying out a process at constant temperature and pressure? Can you write it down just in the terms of state functions, right? So the idea here is that the things in red are state functions, while the things in blue are path functions. So Clausius inequality is nice, but it tells you something about a state change in a state function relative to change in a path function. And the question was, could we have written it down, this condition for spontaneous change? Could we have written it down in terms of purely state functions? And for that, we introduced the notion of free energy, of Gibbs energy and Helmholtz energy. For constant temperature pressure, we wrote down, yes, this is equivalent to saying that dg at constant temperature and pressure is less than equal to 0. And that is something which it's easy to forget. If you're in the middle of the semester, maybe you remember, but a few years from now, again, you're working at some company or whatever, trying to design a fancy drug, you might think ds positive, therefore dg also might be positive. No, dg is negative. And what is g over here? Here we define g as h minus ts. So notice here I introduced h, which itself is a state function defined as u plus pv. Why did we define h? When I do a full recap of the semester in the last week, we will go over that, but you should remember the reason to define H is because that is the same as heat given to a system at constant pressure. So this Clausius inequality is equivalent to saying dG at constant temperature and pressure must be going down for a system, and at constant temperature and volume, it's dA which must be going down, where A is yet another state function defined as U minus Ts. These state functions are mathematical quantities. They are our ways of representing the system depending on what is it that is being held constant. If you want to be like, oh, I can see the math, but I really want to have a more grasp into what does it all mean, well, then that is the equivalent of saying, I really like Beethoven's Ninth Symphony, but I don't care to read the sheet music. I wish I could just have a good feel for it without the sheet music. Maybe it's possible, but if you want to play it, you better know how to read the sheet music, right? So this math is like the sheet music for thermodynamics. You need to be comfortable with math. Once you become comfortable with math, you keep looking at it, suddenly you will see that it is not that far from intuitive physical concepts. Even though to someone who is not taking this class, this half a page that I wrote down might be, if you showed it to your grandma and asked her, grandma, is this chemistry or is this math? Now your grandma might be very smart, so this is assuming your grandma hasn't taken a science degree, or your grandfather, not to be sexist here. Let's ask someone who doesn't have a science degree if this is chemistry or math. They would probably tell you, this is math, this is not chemistry. What's this got to do with chemistry? But here it's actually very, very physical. It's very, very physical chemical, right? You have lots of concepts involved here. So this is why we introduced the notion of G and A. They capture our condition for spontaneous change without talking about path functions. And that's kind of nice about them. At this point, we introduced a very important relation which takes the first and second law, which takes the first and second law and puts it together in one form. And that's the integrated first and second law of thermodynamics, which says du is equal to TdS plus dW. And if you have only pressure volume work going on, which is the form in which we are using it most of the time, then du is equal to TdS minus PdV. This is our integrated first and second law.
I think you're frozen.
Yeah, I did, please. Sorry about that. So, no, it happened. So if you take the stuff in green on the top, which is first law of thermodynamics and second law of thermodynamics, and you mix it together, then you get the integrated first and second law of thermodynamics, which includes information about both first and second law. This equation in the black box over here, this is really complete. This has all the information that you need. And this is telling us that the best way to think about U is as a function of S and V. Because earlier, before our entropy, before our second law of thermodynamics, we were not thinking of U as a function of S and V. We were thinking of U as a function of T and V, right? And that wasn't complete because you didn't have the second law of thermodynamics there. There was loss of information. Now you have complete information with U of S comma V. So this is good. And this led us to our whole discussion about Maxwell's relations and things like that, right? Because we have a total differential, so we should be able to say something about how these partial derivatives talk to each other. And again, when I do the full review, I will talk about that, but I want today to get us to chemical potential so we can keep talking about phase diagrams. And now we can use G, which is equal to H minus Ts, which is equal to U plus PV minus Ts, and we can write down dG is equal to du plus PdV plus VdP minus TdS minus SdT. And what do we get from all this? From all this, we get a relation for dg, which is VdP minus SdT, right? So this is also integrated first and second law of thermodynamics. dg is equal to VdP minus SdT. And similarly, we wrote down expressions for H and expressions for A. Remember? So we did all that. And this tells us that the natural variable for G are pressure and temperature, right? So what are the things that are being varied in order to look at it, if you want to consider both first and second law at the same time? There is, however, something missing in U of S comma V and G of P comma T. Let's start by focusing on G of P comma T for the simple reason that in thermodynamics, we are often interested in experiments happening at constant pressure and temperature. So we wrote down dG is equal to VdP minus SdT. And we said that G is a function of pressure and temperature. What are we missing over here? What is the obvious thing that comes to mind that we are missing over here in this description? We say these are the natural variables, but what do you think? I'm asking you. Composition, exactly. We have ignored the fact that the composition might vary. In fact, we have just looked at a one composition system. We have completely ignored that we might have a system made up of A and B and C, where N, A, N, B, N, C, these are variables that could be varying. We have not account for any of that, right? Instead of A, B, C, actually, let's call it N1, N2, N3. So we can add more of things, right? So we could have many, many components in this system. So we want to think exactly, we want to think of G, not just as a function of P and T, but as a function of N as well, as a function of what if the composition is changing. How do we do that? The way this is done, and this is why chemical potential is confusing. It sneaks in from a very, very mathematical perspective. It sneaks in as just some peculiar thing about a partial derivative, and yet it becomes so profound. And phase diagrams are really all about chemical potential. So what does this mean? We had dG. So let's take a step back and think about G as dG when dG is a function of PTN. How would this be written in a general setting? This would be written as partial G by partial P at constant T N dP, right? Plus partial G by partial T at constant P N dt plus partial G by partial N P T dN. Now for this third term, we have to be careful because this N is actually a bunch of variables on its own. It is N1, N2, N3, right? So this thing is actually partial G by partial N1, dN1, where you're holding constant N2, N3, N4, plus partial G by partial N2, dN2, where you're holding constant pressure, temperature, N1, N3, N4, dot, dot, dot. So it can be written in the mathematical form. And now we realize that the variation with dP over here has to be the same as this V. So this term has to be the same as volume. So we can write this down as VdP because we already had that. We know at constant number, it must reduce to what we had earlier. So we know this is VdP. Similarly, partial G by partial T must be the same as S, or minus S, sorry. So we have minus S dt. And now this other term can be written using a summation form as I going from 1 to k, depending on how many components you have in the system. Let's say you are going from N1 to Nk. Partial G by partial N Ni at constant temperature and pressure, and all other things kept constant except that I that you're differentiating with respect to, multiplied by dNi. And this is how we get to our chemical potential. This thing that you have over here is our definition of chemical potential of the species I. Is that P at the top of the summation? It's K, sorry. Number of components in this system. We have a K component system, okay? And this is our definition of I. The chemical potential of species I is the partial derivative of G with respect to number of moles of I at constant temperature, pressure, and all other NJs with J not equal to I. This is how we define chemical potential. It's sneaky, it's mathematical. It comes like just some strange mathematical thing, and it turns out to be super, super useful. We derive this in context of, so now we can write down that dG is equal to V dP minus S dt plus, instead of dangling, so this complicated looking partial derivative, we are just going to write it as I is equal to 1 to K mu I dNi. That's simpler to write, right? So now this is our integrated first and second law of thermodynamics for a system with variable composition. Now you could have asked the same thing, same question could have been asked about U, right? Earlier we wrote down U as a function of SV, but that's true only for a constant composition system. What if you also have varying composition here, N1, N2, and all Nk? In this case, you will now write down du as a function of Sv. Let's go to next page to work with U. I'll leave this just for a moment if I'm writing too fast, so you can, you don't really have to copy, the notes are online. So we have du as a function of Sv and N1, N2, Nk, everything, right? So Sv, N1, N2. So again, this would be partial U by partial S, keeping V and all the N's constant at multiplied by ds, plus partial U by partial V, keeping S and all the N's constant multiplied by dV, and plus summation I is equal to 1 to K. Now we will have partial U by partial Ni at constant S and V and Nj not equal to I multiplied by dNi. So the thing that I showed in class last time, and you should go and look back at your notes because I did it in detail, is to show that this term over here is also the same chemical potential that we defined earlier. This is the same as this, even though it looks like other things are held constant, it is the same. So the chemical potential could again be defined as partial U by partial Ni at constant entropy and volume and all Nj not equal to I. And this is exactly the same as partial G by partial Ni at constant Tp and Nj not equal to I. This is something which is important you derive it, and it's been, sorry, it's been done in class. It's been done in class that why are they equivalent? The best way to look at it is to start from dg and then go back to the expression for du. And similarly, you can write down something in terms of A, and just to be not make a mistake here, for A, it will be partial A by partial Ni at volume and temperature and Nj not equal to I, and you can write it down for enthalpy. So that's our chemical potential. It can be defined as the partial derivative of a different number of state functions. It can be defined as the partial derivative of internal energy, or the enthalpy or the Helmholtz energy, depending on which state function you are using, the variable that is being held constant changes. If it is potential energy, S and V have to be held constant. If it is Gibbs energy, P and T have to be held constant. If it is Helmholtz energy, V and T have to be held constant. This over here is the most popular form, partial G by partial Ni at constant T and P. There was a parallel discussion we had about molar quantities where we saw that this is the same as G bar. For other things, it is not the same as U bar or A bar because partial molar quantities are always defined at constant T and P, right? That was the definition of partial molar. And you can see it coincides with the chemical potential only for G, not for other things. So let's focus on this one. Let's focus on mu from G. Why? It's not that the other things are not correct. It's just that this is the form in which it is more popular. Any questions so far?
Professor Torre.
Yeah.
I was just wondering, how would you see chemical potential in like an experiment? Because I know, at least for our paper we're doing the paper on carbon nanotubes. They talk about using a form of chemical potential to determine how much water actually flows through the nanotubes. And I was just kind of trying to visualize in my head how you would like get that in an experiment, or how you would actually like how you get a value out for that. What it would represent.
Sure. Let's talk about the chemical potential of students in 481. You are all disappearing as a function of time. When the semester started, 75 of you came to class. Well, the first lecture, maybe 95 of you came in class, right? Now there's 50 of you. It's stabilized around 50. When I speak to other professors, their classes, they are getting 20% attendance in Zoom. So chemical potential, what I'm trying to say here, you get it from looking at how the mass is moving. So by seeing whether the mass, so I'm looking at the number of students inside the classroom and number of students outside the classroom. And if I see that the number of students inside the classroom tends to be increasing with relative to the number of students outside the classroom, that means the chemical potential is lower in the classroom. Okay? So mass always, let me write it down, mass always travels in the direction of lower chemical potential. Okay? Does that make sense? We derived this in one of the lectures. If you go and look at it, we derived this. We showed that if you have a imbalance of chemical potential, you will go in the opposite direction. So mass, so first of all, you can tell about the sign of chemical potential by seeing where is the mass traveling. If mass is traveling from outside to inside, it means the chemical potential is lower inside. That's why it's called potential. It's just like gravitational potential, right? How do you measure which direction are you moving? So this tells you the direction of chemical potential. If you really want to get the magnitude of chemical potential, then you have to measure G. Measure G for magnitude. How do you measure G? Well, calorimetry, right? That's why we derived all those wonderful relations. For example, and I'm just writing one way of doing it, there could be other ways. A calorimeter could give you CP, right? From CP, you could calculate S, correct? By looking at S can be obtained from CP. We wrote down the full expression for this, where if you know CP as a function of time, how do you get S? If you know S, you have this very nice relation that partial G by partial T at constant P is equal to minus S, you can get the G. And so with calorimetry, you can use your thermodynamic skills to get to free energy. And that's how you can get the magnitude of chemical potential. Now, that's the second point here. The first point, however, is more important, that mass travels in the direction of lower chemical potential. That's something you should not forget. That's what you can quickly say whether this is lower or higher chemical potential just by seeing the direction of mass transfer. And you might see that some oxygen is traveling in one direction and nitrogen is traveling in another direction. So you can see that the chemical potentials are different for them. And so that's my answer. Okay, does it help?
Yep, thank you.
Professor, can we look at this like in a context of like biological systems? So say like you had a cell and you know how diffusion happens. Could you say that like inside the cell, the chemical potential is lower?
Yeah, so that's actually a really good question. You know why? Because in general, you should be able to say that. But you know something funny about biological systems? They are not at equilibrium.
Oh yeah, okay.
We are producing entropy, right? We have the arrow of time killing us. That's the strangest thing about biological systems, which is what defines life. You know, life is not at equilibrium. So you have to be careful. But that said, non-equilibrium is so hard to capture that most of the times we just assume that let's say it's kind of equilibrium, so let's use our equilibrium thermodynamics to study things. And that's how people do, and it gets you quite far. But if you really want to be careful about biological systems, you should consider that it is a non-equilibrium system. Then you have to worry a bit more. The way to deal with that and then is to consider not just the cell, but the environment of the cell. And then you say, okay, at the time scale, I am interested in maybe the cell plus its environment and its equilibrium, and we can use equilibrium thermodynamics. But in general, you should always question whether equilibrium applies or not. If it does, which is almost never the case, then you can directly use things. If it doesn't, you should think about how far are we from equilibrium. Okay, good. So this is our definition of chemical equilibrium. Let's focus on mu from G. So we wrote down dG is equal to VdP minus STT plus summation I is equal to 1 to K mu I dNi. We then showed that G is also equal to summation mu I Ni. I'm not proving it is today. Check notes. This was an argument that we went through looking at properties of an extensive system where we showed that G is equal to mu I Ni. This is something that trips people off. And by comparing this equation with this equation, we derived something called Gibbs-Duhem equation, which we haven't really used so far, but it is something you will see sooner or later. So the differential form for chemical potential is important. It tells you how things vary, how the free energy varies. But this equation over here is also very important. Why? Because it tells you that G for a K component system is given by mu1n1 plus mu2n2 plus mu K and K. Now, if let's take a step back and go back to a one component system. If you had a one component system, then G, and again, remember this equation is true not just at constant temperature pressure, it's true all the time. It's a powerful equation. We derived it carefully. There was a subtle argument that we went through to derive it. If you don't remember the derivation, that's okay, but you should not forget that for G, it is mu I and I summation. There is no derivative in this one. If you had a one component system, then what would G be? Let's say the component is num1, its name is 1. Then it would be mu1 multiplied by, or actually if it's a one component system, then we don't need to write subscripts, right? Then it's simply going to be G equal to mu n, right? Because all of these other ones will disappear. They will be 0. You have just one component system. So it would be mu1 n1 because n2 is equal to n3 is equal to all of these are 0. And I'm just replacing n1 and calling it as n because it's a one component system. This gives us yet another interpretation of chemical potential. Chemical potential is G by N for a one component system. For a one component system, chemical potential is the molar Gibbs energy, but only for one component system. If you have a multi-component system, then mu is partial G by partial Ni at constant temperature pressure and J not equal to I. And that is the main take home of this recap. This is chemical potential. And look, thermo is complicated. You cannot always expect that you can derive everything in a flash. It won't happen, but certain concepts you should remember. For a generic K component system, chemical potential is the derivative of the free energy with respect to variation in the number of moles of a given component. For a one component system, it is just G divided by N. So, okay. So that's chemical potential. The other thing I want to review quickly is the second popular topic that some of you protested you don't quite understand. And that's frankly because we did not go over it that much, which is the concept of fugacity. How did fugacity come into the picture? So fugacity came into the picture again by starting with our integrated first and second law of thermodynamics. We wrote down dG is equal to VdP minus SdT. Therefore, partial G by partial P at constant T, partial G by partial P at constant T is equal to V, correct? Therefore, we can write down, we can integrate this equation and say that G is equal to G naught plus integral of V dP going from some pressure P naught to some pressure P if T is equal to constant, right? If T is not constant, then we have to worry about how to deal with T. But if T is equal to constant, we can write it down this way. This is quite generic. This holds true for anything. We haven't assumed any ideal behavior over here. So let me write it down again. We just wrote that G is equal to G naught plus going from pressure P naught to P integral V dP if T is equal to constant for any material. Now assume ideal behavior. Then we can say PV is equal to nRT or V is equal to nRT by P, right? Therefore, G is equal to G naught plus integral P naught P, and volume is nRT by P, and we are talking about constant temperature, so temperature can be brought out. nR by P dP, nR can also be brought out, so this becomes G is equal to G naught plus nRT ln P by P naught, or per mole, if we divide by N, then G bar per mole is G naught bar plus RT. How do I define P naught? Some reference pressure, P naught, some reference pressure. Typically, I would like to define it so that it is 1 bar in the units of P. So if you're measuring P as in units of bar, then it's convenient to define P naught as 1 bar. The reason being that it just goes out, you are left with LNP. So it's some reference pressure. This equation is true for ideal gas. Okay? Now, with your superior understanding of chemical potential, you can say that for a one component system, I know that the Gibbs free energy per mole is mu, right? So we can also write it as equivalent. Did you forget the ln in the ideal gas equation? Oh yeah, sorry. Mu is equal to mu naught plus RT ln P by P naught. For one component system ideal behavior, this is true. And this also confuses people. It used to confuse me earlier. Wait, how did you get this? Now, this is only true for ideal behavior, right? For most things are not ideal. Most things are not like ideal particles. They have finite sizes, they have interactions between them, quantum mechanics might hold true, all kinds of funky behavior might happen. Most things are non-ideal. In fact, everything is non-ideal. you might get to ideal behavior at very high temperatures and low density. So what people said is, if I measure my G versus pressure at a constant temperature, and I just make some observation over here, and then I say that at a particular pressure P naught, my G is G naught, okay? At some reference pressure P naught, my G is G naught. And then I, instead of this, so now I can look at this and subtract out the G naught, right? I can plot G minus G naught versus pressure, right? I can, instead of plotting G, I can just plot G minus G naught. For an ideal gas, we know that G minus G naught should look like RT ln P by P naught. If ideal, how will that look like? That means like a logarithmic curve, right? Log of pressure. How does log of pressure looks like? I think it looks something like this, if I'm not right, if I'm not mistaken. For a non-ideal gas, it won't look like a log. Maybe it will look something like this. So what people said then is, let's call this function, this blue curve that you get by calculating G minus G naught, let's call that in the non-ideal case as RT ln F by P naught. This is how we introduce fugacity. So this F is fugacity, which varies with pressure. It's a convoluted way of defining it, and the only reason people did this is so they can still write an equation that looks like G minus G naught is equal to RT log of F by P naught, where F has in principle nothing to do with pressure. Only for an ideal gas, F is equal to pressure. For a non-ideal gas, F is equal to, let's get this notation right. Phi times pressure, where phi will depend on pressure. It will be some function of pressure. It will vary with pressure. And it is called our fugacity coefficient. And then we talked a little bit about how this coefficient might be less than 1 or more than 1, depending on attractive forces or repulsive forces. So this was our fugacity. We didn't use it. The reason we didn't use it is because, well, we have enough to learn with ideal gases. You know, its life is already complicated enough. If we can master ideal gases, the reason I introduced this is because you will see it showing up in literature. And the reason it shows up is because people like this G minus G naught is equal to RT ln form so much that they are desperate to use it. And they say, well, even though it's not pressure over here, whatever fits this G minus G naught as a function of pressure, let's call it as the fugacity. It's just a fit. What you have done is to look at, so if you look at G minus G naught is equal to RT ln F by P naught, what does that mean? That means if you take the exponential of, if I bring the RT over here, then it's like this, and this means that e to the power G minus G naught by RT is equal to F by P naught, right? So you can think of fugacity as being defined for some reference pressure as, in a way, this is our definition of fugacity. For an ideal gas, this will be the same as pressure. For a non-ideal gas, it will be different from pressure. But if you monitor F divided by pressure, as in this equation, you can get insight into whether attractive forces dominate or repulsive forces dominate.
I have a question.
Yeah, go ahead.
So on the last page,
Mhm.
the one for this one, so you wrote that for a one component system in ideal behavior, you could substitute mu in. So is that only for ideal behavior, or is it just like only for one component, or is it very specific?
Well, for a good question. So for a non-ideal behavior, once again, you will have mu is equal to mu naught plus RT ln F by P naught. So this is one component, non-ideal. Okay. For multi-component non-ideal, life gets very complicated. First, let's just think about multi-component ideal. Multi-component ideal is exactly what we dealt with in our study of solutions, right? That's what we did over there. When we did our, let's see, where do I have it over here? So the next thing up will be multi-component and ideal, right? Multi-component and ideal is where we now have to think about A, and we have to say, if we have a component A, then we have to say mu A is equal to mu A naught plus RT ln partial pressure of A divided by P naught, and for mu B is equal to mu B naught plus RT ln partial pressure of B divided by P naught. Remember, this is, so if you go back and look at your thermodynamics of solutions when we started, just mixture of ideal gases, this is what we wrote down. So it's very similar, but you have replaced pressure with partial pressure. Now on top of this, if you have non-ideal behavior, you can still use the same equation, but it will be something like a partial fugacity, and we will visit like later. But this is how we do for a multi-component system. Does that help?
Yes.
Okay, good. You don't have to say yes, you can keep arguing, that's okay. I really like students who like to argue with me because it keeps it real for me. As long as it is not just an argument for the sake of argument. If you think it's not clear, you should stop me, and we should make sure that it's clear. Okay, so I had thought this review would take less time, but that's okay. It's important to understand chemical potential. I'm going to start the next topic now, and we will resume next time. We have only 7 minutes left, but I want to give you a flavor of what we are doing here. So the flavor of what we are doing here is to understand liquid and vapor equilibrium in two-component system. How do they exist together? We looked at liquid and vapor in a one-component system, right? We drew a pressure, temperature, phase diagram for water. And remember, we spent a lot of time figuring out as to why for water, this curve slopes negative, right? So we had our which, anyone remembers which phase was which? This was solid, this was liquid, this was vapor, right? But this was for a one-component system. For a two-component system, how will it look like? If in water you have added a certain solute, now it's no longer a one-component system. You can change the concentration of the solute. So this was for a one-component system. For a two-component system, we have to now think about the composition. And the best way to think about the phase diagram for a two-component system is to not look at pressure, temperature, but to look at temperature and composition. That's the most popular way. So let's say our two-component system is made up of A and B. So on the bottom axis, we will talk about the mole fraction of B, and that will go from 0 to 1. And we can think about this phase diagram. And what we are going to study are phase diagrams that look as follows. This is the simplest two-component phase diagrams, where you have vapor on top, liquid in the middle, and vapor plus liquid. What did I do over here? Vapor plus liquid in the middle and liquid in the bottom. And we are going to understand how does such a phase diagram come to happen. So in this, our process will be quite systematic. We will start at a bunch of temperatures. We will start at a very high temperature T5. We'll go to some temperature T4. We will go to a middle temperature T3, then yet another lower temperature T2, and then finally we will come to T1. And we are going to think about the free energy of the vapor phase and the free energy of the liquid phase at all of the different temperatures. Okay, so let's start with the free energy of the let's start at T is equal to T5, which is very high. Okay, I'm not rushing through this. I'll go through this again, but I think it's useful if we have a first look at it today, because it's one of those things that's quite simple if you pay attention, otherwise it can be confusing. So at a very high temperature, what do you expect between G vapor and G liquid? Which one should be lower at a very, very, very high temperature? Very high temperature, Anthony.
G vapor.
Eh?
G vapor.
G vapor. Why? Because the direction of spontaneous change is lower free energy, right? Remember, exactly, dG should be negative for spontaneous change. So at a very, very high temperature, you will have the G vapor curve looking like this, and the G liquid curve will be somewhere higher. Why did I draw this shape? Well, remember, it goes to the slopes at both ends are going to be minus infinity and plus infinity for both of them. And we saw in our regular solution model how it curves in the middle and then goes up. Now we have to think about a slightly lower temperature. So I'll draw just below it. In fact, I'm not going to be able to fit. I think I will remove. It's okay. We'll go to another page. So let's look at T is equal to T4. Now, what's going to happen to both of these free energies? What do you expect will happen to GV at T4, which is lower than T5? Will the free energy of the vapor curve move up or move down respect to this one? Will it move up or down? Any ideas? Up. Why? I got Matt. Come on, Matt, help me. Why should G move up?
Because there's less energy in the system.
Let's be mathematical, Matt. Let's talk about partial G by partial T at constant pressure. What do we know about this?
It's a constant, or it's volume.
It's minus S,
No.
right? What do we know about S? Is it positive or negative? Entropy is always positive, right? So partial G by partial T at constant P is always negative. What does it mean? It means that the change in G multiplied by the change in T is with a negative number. So if delta T is negative, that is T4 is less than T5, then delta G must be positive. The sign in delta G must be the opposite of sign in delta T. So you had both the right answer, but the logic has to be a bit more rigorous. This is why we get it. So both will go up. Now, the other question is which one will go up more? So we know that partial GV by partial temperature at constant pressure is equal to minus SV. This is vapor. And we know that partial GL by partial temperature at constant pressure is equal to minus SL. And both of these entropies are positive. So the slope is negative. As you decrease the temperature, the free energy goes up. Which one will go up more, vapor or liquid? Anyone wants to help?
GL. Yes.
Which is higher, SV or SL? Which one has a higher entropy?
SL.
SV, the vapor has a higher entropy than liquid, right?
Yeah.
Right? Vapor is like, ooh, I'll go anywhere. I don't care. I'm going to do whatever you want and whatever I care for. This directly means that this slope is negative, but on top of that, this negative number that you have over here is bigger for the vapor than for the liquid. So the vapor will move up relative to this curve. It will move up somewhere, and I can't really plot everything in the same picture. And the liquid will also move up, but the point here is that the liquid will move less relative to the vapor. So they will get a bit closer. So I'm going to end it like an episode from a detective show or something. So next episode, GV, GL, or GV will catch up with GV. GV will catch up with GL as temperature is lowered. So the point we are building here, can you state which G is on the top and bottom for both graphs? This is GL, this is GV. This is GL, this is GV, okay? At a very high temperature, the difference between them is large. At high temperature. As the temperature goes down, the difference between them starts to reduce. Why did the difference between them reduce? Is because both of these curves move upwards due to entropy. The lower curve, the liquid curve, however, moves a little bit while the vapor curve moves a lot. As we reduce the temperature further, you will see they start to cross. So at T5 and T4, the vapor is more stable with respect to liquid at any composition. At the middle temperature, we will start to get into this funky region. So next time I will work through this argument again. It's a beautiful, simple, and powerful argument that how these curves move ahead. And it really boils down to this nice equation. So this is where we will start next time. And I will have office hours next Monday, so we can discuss more then. Okay, see you all.